So I posted the notes packaged, the whole package of notes for circular motion already. So it's in the files tab if you haven't done that already. So let's go through the first lesson, I guess. Okay. So this is it's a lot of dynamics and free body diagrams and stuff like that. It's just applying it to a circular motion. So anything traveling in a circle or in an arc. So it doesn't have to be a complete circle. Anything that's like moving, I don't know how to explain that, at an arc is the best word to use, is traveling in circular motion. So we'll look at things like that. So so we're going to apply kinematics and dynamics to this. So let's consider a mass on a string being twirled in a horizontal circle. So we're looking at, like, this circle here is a top view. And so the object's going around in a circle horizontally. So speed is defined as d over t, so the distance over time. In circular motion, we define time as a period of motion that it takes to complete one rotation, and we use capital T for period. So it, like, if we were to, let's say it starts here and then goes all the way around that way and then ends here, like the time it takes to get from one point to the other is one period. Okay, so one capital T. And then how far does it travel in one rotation? Well, if it completes one whole circle, then it does the whole circumference. So how far does it travel? It travels a circumference. And the circumference of the circular path is going to be 2 pi r. And so if you put these together, if you apply this to the formula for speed, v equals the distance it travels, which is 2 pi r, in a period of time, like that. So that's our first formula for speed. Now, keep in mind that this is average speed, okay, because we're just taking from one point to the other. It could go faster during like one half of the circle and then speed up for the other half, but we're just taking how long it took to complete one circle. It doesn't matter. Each segment doesn't matter. We're just looking at the whole thing. Okay, so we figured out its speed, but is the mass accelerating? Okay, now remember that acceleration is defined as delta v over t. So we're finding average speed and we're assuming it's a constant speed. So if speed doesn't change, then you would think that it's not accelerating. But look at the formula again. Acceleration is a change in velocity over time. And velocity is defined as a change in speed and position. Okay, so velocity, speed, and position. So the position is changing all the time. Okay, so at one point the object's going that way, at one point the object's going that way, and then that way. So it's always changing position. Okay, so notice that the direction of the velocity at any time is perpendicular to the path traveled. Okay, so and what we call this is we call it tangent to the circular path. Okay, so at any moment the velocity is perpendicular to the path, so it's moving at a tangent. And so so even though it may be traveling at a constant speed, anything traveling a circular path is accelerating. because the direction of the velocity is always changing. Okay. I totally forget what this formula is. Time to look up my formula sheet. Maybe I'll just go to Teams. Give me one sec. Files. There it is. Okay. I think there's a definition here somewhere, but where are you? Okay. So we have our formula for speed, v equals 2 pi r over t. And then the next formula for acceleration, I'm not going to derive it or anything like that. That's done right here, but I'll just give it to you. So it's a, oh, that's a huge A. A C, so I'll define what C is in a sec, equals, which one do I want to give first? So there's two formulas for this. There's V squared over R, and there's also 4 pi squared R over T squared. Okay, and then for the derivation, it's maybe do I want to do it? I don't want to do it. It's confusing and yeah, don't worry about it. So all you need to know is that it's a relationship between the speed at any point and then like the arc length. So like if you have R and let's say R and this is a distance of R, then you can figure out through acceleration and change in velocity how it can be this. So we're not going to do that though. Okay, just we have formulas, we don't really need to know where they come from. So it's worth noting from the above derivation, we didn't do it, that the direction of the change in velocity is always, okay, so this part we are going to do. So if you look at any point, so let's say we have the velocity going that way, and then the velocity going that way. Okay, so this is our VI and this is our VF. If we do delta V, then this is going to be VF minus VI. So VF is going this way, and VI is going, I don't really know how to draw this. So like, let's go like that and like that. So VF and then minus VI. So that means we're going this way. I'm trying to draw it as close as possible. And then that arrow right there. Now, if you were to look at both of those, this delta V is actually pointing. So like if you were to draw like that, so the difference between those 2 points, the change in velocity is actually pointing to the center of this circle. So regardless of where you draw this, so like if I were to draw it again, it's like, conversation. Is it possible that VI going opposite directions? I don't understand that question. Sorry. So Kanwu, you need to rewrite your question in a way that I understand, because I don't quite know what you're saying. Is it possible that VI going opposite directions? I'm not quite sure what you mean by that. Okay, so you'll notice how, like, if I have VF here and VI and VF, the change in velocity, which like occurs in the middle, is pointing to the center. Notice how this delta V is pointing to the center. So wherever you draw it, the change in velocity is going to be pointing towards the center. So change velocity is always pointing towards center of circle. Okay. Therefore, the acceleration of an object in the circular motion is always towards the center. And this is the definition of centripetal. So centripetal means center seeking. It's always pointed towards the center of the arc. Okay. So if something is traveling in a circular path like this, there has to be acceleration. So like this one would have a center of a circle right there. At all times, the acceleration is pointing towards the center of the circle. And if the acceleration is always towards the center of the circle, there has to be a net force towards the center. Okay, in order for there to be acceleration, there has to be a net force. And so if acceleration is always pointed towards the center of the circle, the net force is always going to be pointed to the center of the circle as well. Okay, and this is known as centripetal force. So we have centripetal acceleration, or acceleration that is always pointed towards the center of the circle. And we have centripetal force, the force that's always pointed towards the center. Now, this isn't a new force. It's just a net force. That's all it is. Okay, so if we apply this to different concepts, different scenarios, if we have a mass that's twirled in a circle at the end of a string, so let's say we're swirling it in a horizontal circle, so we're looking from below, and this is the string, okay? At any point, the force that's, like, you can imagine that the tension is, oh, I don't want to draw an arrow. The tension is always going to be this string, peace symbol. It's always pointing towards the center, but the thing that is pointing towards the center is tension. Okay, if we're whirling it by a string, then we would say FC equals tension. Okay, think about a car rounding a corner on the highway. Okay, so you have this car that's rounding a corner on the highway. There's the car. Okay, its force that's pointing towards the center is friction, and so we would say FC equals FF. Okay, now let's think on a bigger scale. When the moon orbits the Earth, the centripetal force is caused by, well, the fact that the moon orbits the Earth is caused by gravity. So in this case, FC would equal FG. Okay, and let's think about one more example. Let's say we take that rope and we're twirling a mass, but now we're twirling it in a vertical circle. Okay, so it's still attached to a rope. At this point right here, you have tension going this way, you have gravity going this way. So in this case, FC would equal tension. At the top of the arc, you have tension going down, but you also have FG going down. And so your FC would equal FG plus FT, because it's both. And then at the bottom of the circle, you have tension going up and FG going down, and your FC would equal T minus FG. Now notice how my FC in this case is going up, T is going up, FG is going down. Here it's going down, 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 so I'm just saying it's all positive. And we'll get into this further, but I'm just showing it to you now so that you realize that it's not a new force. FC isn't something. It's just a net force pointing towards the center of a circle. That's all it is. Okay, so it's still dynamics like we did before. The only difference is it's moving in a circle. In terms of the centripetal force to find the forces, we're just going to apply Newton's second law, which is F equals ma. Okay, so we had two formulas for AC. So if I do FC, centripetal force, instead of V squared over R, which is A, it's going to be mv squared over R. Okay, and it's instead of 4 pi R squared over T squared, it's going to be m 4 pi squared R over T squared. I can't remember which one that is. 4 pi squared R. Okay, yeah. Okay, so all you're doing is putting an m in front of the AC, and that's it. Okay, so let's do some examples. This first one is, I have to draw a picture of it because it doesn't really make sense. So imagine a table like this, but in the middle of the table there's a hole, and then you have a mass like this, and you're attaching it to a string with a mass hanging like that. Okay, so that's the side view of what's happening. Now the top view of what's happening is we have the circle in the middle, the mass hanging, the mass like that, and then it goes into the circle and it's hanging below the table. Now what we're doing is we're throwing the mass around so that it does this. Okay, it's in a circular path. So if that's true, if the mass is going to be, and you could try this by throwing, it's not going to be frictionless, so it won't work. But if you threw a mass in an arc, so think about this. Okay, here's the Earth, here's the moon. Okay, why doesn't the moon just fall towards the Earth? It's FG, right? Usually things that have FG fall towards the Earth. Why is it not falling towards the Earth? The answer is because the moon is actually going that way. Okay, so it's moving at a tangent to the Earth. So instead of the FG causing a falling force, it's causing a centripetal force. And so it's causing the circular motion of the moon. And this only happens if the moon, like, I don't want to get into like how the solar system was created or whatever, or came into existence. The only way this happens if the moon actually started moving that way when it came into contact with the Earth. Okay, and it could happen with it. Yeah, again, I don't want to get too much into it, but you just have to understand that the moon is always traveling in a circle. Okay, because it's moving tangent. So if you throw this mass tangent to the center of the circle, it'll keep moving tangent to the circle because there's a force pulling it towards the center all the time. Okay, and that's caused by the hanging mass, this FG right here. Okay, so that FG is going to cause a tension in the rope. That tension is going to be over here, and this is going to be our FC. Okay, this tension right here is our FC. Okay, so the 0.5 kilogram mass sits on a frictionless table and is attached to a hanging weight. Whirled in a circle of radius, calculate the centripetal force. So if you look up at our centripetal force, we have two options here. The first one is mv squared over r. So we have mass, we have v, and we have r. So that's one we're going to use. Okay, we don't need to use 4 pi squared r over t squared. We don't actually have t, so we're going to use mv squared over r. FC equals mv squared over r. So that's going to be 0.5 times 2.3 squared over 0.2. 2.3 squared divided by 0.2. So this is going to be 13.225 newtons. And then calculate the mass of the hanging weight. So if our FC is caused by if our FC is the tension, but the tension is caused by the FG, then they're equal. So the FG of the hanging mass is 13.225. Okay, so mg equals 13.225. Stop me if you have questions, please. So the m is 1.35 kilograms. Okay. Next example. Car traveling at 14 meters per second goes around an unbanked curve in the road. Unbanked means it's level. It's not at an angle. With a radius of 96 meters, what is its centripetal acceleration? So in this case, we're not doing force, we're doing acceleration. And again, we have V and we have R. So we're going to go AC equals V squared over R. So that's going to be 14 squared over 96, which is 2.04 meters per second squared. And then what is the minimum coefficient of friction between the road and the car's tires? So the car that's moving in the circle, the FC is due to friction. Okay. Excuse me. So imagine your road. Here's the car moving in a circle. Like the car is turning its wheels, and like the only reason you can turn a car by angling its wheels is because of friction. Okay, you're creating unequal friction on both sides of the tire, so it'll actually turn the car. And so that's what's happening here, but the friction is going towards the center. Okay, so if this is the case, what we can do is we can go MAC equals mu mg. The m's will cancel out. That's why we don't have the mass of the car in the first place. And then we can just plug this in. 2.04 equals mu times 9.8. It's a weird mu. 2.04 divided by 9.8. And we get a mu of 0.21. Okay. Okay. Next one. A plane makes a complete circle with a radius of blah, blah, blah in 2.1 minutes. What is the speed of the plane? So this one, we're going to go back to our first equation, V equals 2 pi r over t. So we're going to go V equals 2 times pi times 3622. And use the pi button on your calculator. Don't use 3.14. Okay, don't approximate it. And then because all of this is in standard units, like all of our, like this, when we put in t, it's already in seconds. So we can't use minutes. We have to use seconds. So that means we need to go 2.1 times 60 to find out how many seconds there are. So that's 126 seconds. And now we can solve it. 2 times, where's my pi button? Stupid new calculator. What the heck? You would think they would make the pi button really easy to find. Oh, there it is. That's not easy at all. Okay. So 2 times pi times 3622 divided by 126, and you get V equals 181 meters per second. Okay, notice how this is meters, 2 and pi don't have units, so that top is meters, the bottom is seconds, so your answer comes out as meters per second. Okay, any questions about any of the examples? It's fairly simple, you just plug things in. Okay, there's something called centrifugal force, which is a fake, well, I don't want to say fake, well, yeah, it's kind of, it's an experienced force, but it's not an actual force. Let's put it that way. Now that might not make sense, so let me try to explain that. So centripetal means center seeking. Okay, it's going towards the center. Centrifugal means center fleeing, so away from the center. So if you think about a car, let's say, the car will be going in a circle this way, but everyone in the car will not be experiencing the same thing. Okay, the car has the friction applied to it, and which is why it turns. But if you've ever turned in a car, you have to sort of lean the other way. Otherwise, you just like if you've ever done a sharp corner or something like that, you have to lean the other way. Okay. And that's because of Newton's first law. Okay. So inertial frame of reference is where Newton's laws are true. Okay. So it's inertial frame of reference just means that it's a non-accelerating frame of reference. So it's the constant velocity. So like if you're on Earth is well, like where you are standing right now or sitting right now is an inertial frame of reference because Earth is traveling at a constant velocity. Okay, it's spinning at a constant velocity and it's moving through space at a constant velocity. So there's nothing you can do to know that the Earth is spinning or not. Okay, we know because of day-night cycles and all that stuff, but you can't just like, you can't jump and then land in a different position because you are in that inertial frame of reference. The Newton's laws are true. Okay, so within that, within our inertial frame of reference, like if you're in a car traveling at constant velocity, let's say, the centrifugal force is actually an apparent force. It doesn't exist, but you feel it still. Okay, and that's because of Newton's first law. Think about a car moving in a straight line. Okay, the driver is moving in a straight line, the passenger is moving in a straight line, and let's say there's a water bottle on the back seat moving in a straight line. Okay, if the car turns, so now the car is going this way, everyone in the car wants to keep going that way. The bottle wants to keep going that way too. Because of Newton's first law, an object moving, or an object at rest will remain at rest. An object in motion will remain in motion unless acted upon a net external force. Okay, so you want to keep moving in a straight line unless a force acts on you. So that force that's causing you to move in the other direction, like this water bottle will slide to that side of the car. You will lean towards that side of the car unless you're leaning towards the center of the car to counteract it, because you can kind of like see the corner coming up. So what happens is you would like lean up against the window or whatever, and then the car is actually pushing you in the direction of the car. So it's the normal force of the car that's actually like, so let's say this is the car and you're right here leaning against, you want to go that way, but the car is pushing you that way. This is a normal force right here. Okay, you would feel it as a centrifugal force because you feel the force going that way, which is center fleeing, but it's just the normal force of the car pushing you in the direction of the car. Okay, so it's kind of confusing, but that's all it is. I see this away from the center. Okay, so yeah, that's all. I drew the picture there that answers that example. So you slide across the street, seeming to accelerate, but you're not actually accelerating. You're just staying in that straight line of the car. Okay, and then you seem to be accelerating outwards, but the car is actually moving you inwards. So it's an actual centripetal force. So yeah. And then I guess we'll do lesson 2 tomorrow. Let me just see. I don't want to do bank curves for sure today. So yeah, let's just do lesson 2 tomorrow. Let me just check the worksheet here. And I'll share the screen so that you can see too. Oops. Okay. Come on, teams. There we go. Stupid. Okay, files. Glass materials. Good motion. So this is like, there's all the review is on there already. You don't have to do that, obviously. We're not even close to that yet. The worksheet package. So you can do that. Just trying to find where. Okay, so you can do the first worksheet, 5.1. Okay, and then 5.2 will be tomorrow. Yeah, so you can do 5.1 today. So for those of you who have not finished yet, finish the momentum test, please hand that in as soon as possible. And then just check the chat. Well, I mean, you'll get a notification hopefully on when I send the progress reports out. And yeah, and those of you who I've contacted who are missing other things, please hand those in as well, because I need to be up to date. So any questions? Okay, so tomorrow we will meet at 8:30 again, and then we might do 2 lessons potentially tomorrow. So yeah, but that's it. We're just going to stop at 1 lesson today. That gives you plenty of time to do the worksheet, and then you'll probably have a bit of time to just relax to get ready for a bigger day tomorrow. So that's it. Have a great day, and I'll see you guys tomorrow.